Hello guys, good evening, morning or afternoon. So today we'll be talking about the last topic for our partial derivative series, and that would be the Jacobian actually, alright? It's not writing, hold up. Okay, there. Jacobian, okay? So we're gonna talk about how to determine the Jacobian, right? And of course, we're of course gonna go through some problems, right? And we're gonna solve them. Okay. So first and foremost, let's talk about a function, okay? And this is a function of f, okay, which is a multivariable function expressed in terms of x and y, okay? And let's just say that we have a function also of u, which is also expressed in terms of x and y, okay? And we have a function of v, which is also expressed in terms of x and y. Okay, we're gonna write it down like that. So v, x and y. Okay, so we have three functions, yeah. So of course we have the function of f that's expressed in terms of x and y, a function of u that's also expressed in terms of x and y, and a function of v that's expressed in terms of x and y. Okay, and of course, since we can express f in terms of x and y, we can also express f in terms of a function in u and v, okay? So this t is actually just basically a way to express the function, right? Considering that u and v are related, right, to x and y, okay? And this means that if we want to find the derivative of x and y, how we're going to find it is more like this. So for example, del f over del x, right? We'd have to use the chain rule, just simply del f over del u times del u over del x plus del f over del v times del v over del x, okay? And likewise, if you want to find for del f del y, it is just simply del f times del u, alright, del f over del u times del u over del y plus del f over del v times with del v over del y, okay? So these are the derivatives, the partial derivative of del f with respect to x and del f with respect to y, and you can see that we've actually just used the chain rule, okay, as we discussed earlier. So we've actually just used the chain rule, okay? And if I were to erase all of this real quick, okay, just to show you what I mean here, okay, if we can write it in a different form, okay? So if you don't mind, I'm gonna erase this actually, just so that I can actually show you what I mean. Okay. So we have the first one, right, for del f over del x, which is just equals to del f over del u times del u over del x plus del f over del y del v times del v over del x, and then for here it's just del f over del y equals to del f over del u times del u over del what was it again, del y, yeah, plus del f over del v times del v over del y. Okay, given that we have a function of f, okay, which is written in the form of, we now write in the form of u and v, yes, we transformed in the form of u and v, and this u and v of course are related to x and y, which is just u is a function of u x y and v is a function of v x y, okay? We're gonna see some examples later, so don't panic about it. Now what I'm trying to bring your attention is what if we wrote it in a matrix form. So del f del f over y written in a matrix form, and of course we'll write all of these in matrix form. So meaning to say that this will be in a matrix, okay, which I'm circling in orange. Okay. Okay, so yeah, who knows this? Actually, if I were to erase this, you can see how these are common. Okay, so let me write it in a matrix form. Okay, so if I write this in a matrix form, what we'll end up having is I'm gonna write this as fx. Okay, so fx means del f del x, right? And fy is equals to what? Is equals to ux, okay, uy, vx, and vy, okay, and then we multiply obviously with fu, okay, and fv. Alright, so if you write it in a matrix form, this is actually what we'll end up getting by the way. This is basically what we'll end up getting, okay? It's basically a system of linear equations. A system of linear equations, right? Which we just written in matrix forms. So matrix form, okay? And later in the matrix chapter we'll discuss more about this, but for now remember that we can write in a matrix form, which can be expressed as ax equals to b, okay, where A is basically a 2 by 2 matrix, your x is basically a 2 by 1 matrix, and your resulting B would be a 2 by 1 matrix, okay? So in this case, this is your A, this is your x, okay, this is your B. Just remember this for now, okay? Don't worry about it. And now I'm gonna erase this just so that we can have enough space actually, because we are looking for space. Okay. So this particular matrix, right, we talked about earlier, this matrix, okay, if you find the determinant of this matrix, okay, to say that del u over del x, okay, del u over del y, del v over del x, and del v over del y, you find the determinant of this particular matrix A, okay, or this is what we call as the Jacobian, okay, this is what we call as the Jacobian actually, okay. And sometimes you can write a Jacobian actually as just simply del u v over del x y, okay, so you can represent it like this. And yeah, that's basically it. That's basically what Jacobian is about. Now what is the point of the Jacobian actually is, let's say if you're given a multivariable function, okay, maybe in terms of, alright, let's just pretend we draw a simple curve, okay, of x, y, and z, and let me use a different color. Let's say for example we draw paraboloid, okay, for instance, okay, a simple paraboloid, right, and then we draw it right here, okay. So in this paraboloid actually that we just drew, let's say if I want to find the rate and change of this u and v, which we consider as our output, by the way, it's all the outputs, okay, basically we can call it a system of outputs, okay, versus, alright, we call here our system of inputs, system of inputs. So like our paraboloid here for instance, right, let's say we want to find the rate and change of the function due to both x and y, okay, because we know the rate and change due to x may be, for example, I'm just saying, yeah, we take like maybe like a different color, maybe like a tangent line for example touching the paraboloid, And maybe for y, it could be this tangent line that's touching the parabola, the tangent plane actually, not line, sorry. This is actually a plane, okay, because we're looking at it one perspective, that's why it's like a line. So maybe we want to see, due to x and y, how will this paraboloid change? How does the values inside the paraboloid will change due to both x and y, both inputs? How is the output changing? Maybe our output in this case is z. Your z maybe is the function f here, relating to the function f. Okay, so that's normally the main idea of Jacobian actually, because previously what we've been doing is always we find the function f, how is it changing with respect to x, or maybe for example in terms of y. Sorry, that was that, my apologies. Y, okay, so we want to actually now find out how is it changing with respect to both x and y, right? We want to know that. So that's the whole idea of Jacobian actually itself. That's the whole shtick about Jacobian, okay? Like what's the, you know, how do we deal with it? Alright? And for Jacobian, right, we also can find the inverse transformation, okay? The inverse transformation meaning to say the J1, okay? So how we're going to find the inverse of that? So let me erase this real quick. Okay. So let me just actually clarify a little bit what I mean by saying inverse here. Okay. So J1 basically is del xy over del uv, okay? So what I mean to say by inverse transformation actually, okay, why they call this the inverse transformation earlier. Alright, so inverse transformation. What I mean to say is that we have a function of x that can be represented in terms of u and v, and of course we have a function of y that can be represented in terms of u and v, right? And they're actually basically the inverted, okay? So they're basically inverted, okay? Whether be it x or y, they're actually inverted from the original. Remember the original we had u as u over xy, v equals to v over xy. So we sort of rearranged it, okay? We sort of like rearranged it. Actually, I wouldn't want to draw direct arrows, but you get the gist, okay? We basically rearranged it. We just flipped the tables along and said, okay, what if we had it the other way around, right? What if we had it the other way around? So yeah, basically that's what it means by the inverted version. And how are you going to find the determinant inverted version actually? Okay, we can of course do the long way, right? Or in this case it will just simply be, if I'm not mistaken, yeah, it would be del x over del u, del x over del v, del y over del u, right, and del y over del v. So that's basically the inverse transformation of J1, okay? And if, okay, because J itself, Jacobian is a determinant, okay? So Jacobian basically refers to a determinant of a matrix. So determinant actually has a value, alright? It can be any sort of like a scalar number, obviously, right? When you do determinant of a 2 by 2 matrix. So if, okay, if our J, the Jacobian, doesn't equals to 0, so that means that J1, okay, the inverse transformation after you inverted, or if you inverted the original equation, right, after you inverted and got this inverted version, okay, is equivalent to the inverse of the J matrix, okay, the inverse of the original Jacobian matrix, right? The determinant of the original Jacobian matrix. Okay, so that's the idea. And if J is equal to 0, that means that uxy and vxy are dependent. Okay, that means they are not independent of each other. Actually, they're related. Okay, and I know this seems a lot to digest at the moment, but let's try some examples. Okay, and let me show you how does this work. Okay, so for instance, let's give an example right away. Okay. Okay, so for instance, all right, let me write here. I have a function. Okay, let me just erase all of this first. I think it'll be easier. Okay, so let's say we have a function here. Okay, this function, we write it in terms of u and v, which is just 2u plus 3v squared. Okay, and we know that u is related to x and y by x squared plus 5y, that's u, and we have here v, which is just 2x cubed plus 4y to the power of 4. Okay, and they want you to find the Jacobian, right? Find the j. Sometimes they write find the j, or in this case del uv over del xy. So how are we going to find it? Okay, so it's actually quite straightforward. So del uv over del xy, okay, is basically del u over del x, del v over del x, del u over del y, del v over del y. Okay, and I think that's how you find a Jacobian. But let's say if you're not so sure, let's say if you do not know that's the correct way to go for this problem. So what I suggest you to do is find the original del f over del x, which is just del f over del u times del u over del x plus del f del v and del v over del x, right? And del f over del y, okay, is equals to del f over del u times del u over del y plus del f over del v times del v over del y. Okay, so if we take these four parts, yeah, this one that I'm underlining, then obviously from here you can easily get the Jacobian. Okay, so sorry, let me use the green color. All right, you can easily get a Jacobian, which is just simply ux uy vx vy. Okay, it's just straightforward, very simple. So this is just in case if you do not remember how to derive the Jacobian matrix. So I suggest you to write the chain rule equations. Okay, so these are the chain rule equations. Okay, so if you write them down, the chain rule. Okay, then eventually you can be able to derive the Jacobian like I did just now, just to be sure. It's a very good way to be sure. Okay, sometimes you don't remember the exact form, so it's always a good idea to write it down. Okay, so how do you find the Jacobian? Okay, so we find ux first. So in this case, our ux would be what? Ux would be 2x. Okay, uy would be 5. Okay, vx would be, if you are differentiating, it would just simply be 6x squared, and vy would be 16. 4 times 4 is 16, y to the power of 3. Okay, so obviously once you do the Jacobian, it will just simply be 2x 5 6x squared and 16y cubed. So what would happen is you of course you find determinant, and remember to find determinant of a 2 by 2 matrix, you just multiply these two terms first, alright, and then subtract with these two terms when you multiply. Okay, so it'll be something like this. All right, so blue goes first, followed by orange. So it'll be simply 2x 16 y cubed, okay, minus 6x squared times with 5. So you will end up having 32 x y cubed minus 30 x squared. Okay, so yeah, that's basically it. That's basically your Jacobian actually. Okay, and if they mention what values of x and y, let's say for our case, maybe they mention x and y to be 1 1, for instance. Okay, a very simple example, 1 1. So what would happen is that we'd have 32, of course, times with 1 and 1 cube minus 30 times 1 squared. So our Jacobian will just be 32 minus 30, right? So it'll be 32 minus 30, which will obviously grant us 1. Okay, so I don't want, sorry, my apologies, it's supposed to be 2. There's a simple arithmetic mistake I made right here. Whoops. Okay, yeah, 2. Alright, so yeah, that's all. Just be careful with arithmetic, yeah. But yeah, that's actually how we find Jacobian actually. We don't really need the original function f, because it's not really needed for Jacobian. Since Jacobian, we just need the function of u and find a derivative respect to x or y, and also likewise the same goes for v. All right, we have the function of v and derive it with respect to x and y. Okay, so that's normally how we'll do the Jacobian. Okay, and let's say for instance you want to check, right, whether let's say for example you want to find a relationship. Okay, let me try to erase this part first. Okay, okay, let's say for example we're given the function, right, the same function as previous, yes, u in terms of x squared plus 5y, v equals 2xv plus 4y cubed, and we are given these values of x and y earlier, right? We discussed about the values of x and y earlier, so let me just erase this. I think we better erase this and then write it here. Okay, so we're given the values of x and y, for instance. Okay, so x and y is equals to 1 1. Okay, now let's say for instance we wanted to find, we're given a representation of x. Okay, so x is maybe equivalent to u cubed plus v squared, and y is equals to randomly, let's give random values, u squared plus v. Well, actually that's not really right. Normally if they were to give you in terms of u and v, you'd have to of course find the inverse. Actually, you have to find what is x in terms of u and v. Okay, and of course what is y in terms of u and v, right? You need to find these two, then obviously you can find the j1. Okay, you can easily find the j1, and I think for this case we know the Jacobian is clearly 2, right? So we can say confidently, if we find the inverse Jacobian of this particular of these values, right, and with the Jacobian matrix is equivalent to the j1 actually. So let's do that. Let's try to find the inverse in this case. So how do you find the inverse? So we found the original matrix a while back, right? So the original matrix was something like this, right? The Jacobian original matrix was determinant of ux, uy, vx, vy. So ux was obviously 2x, uy was 5, vx was 6x squared, and vy was 16y cubed, right? And if we plug in all the values together, we have 2, 5, 6, and 16. Okay, that's the normal Jacobian. Now if you want to find the inverse Jacobian, It's very straightforward. It's just 1 over the determinant. Okay, the determinant we found earlier was just, we cross product these two, right? Which is eventually we got was 2, by the way. And what happens is that we're gonna of course swap the values. Okay, we already found the determinant. So we need to say, to find the inverse for 2 by 2 matrix, we're gonna switch those values. Yeah, so we're gonna switch these two values, by the way. Okay, and we're gonna add negative signs for here and here. So therefore it would be 16, okay, -5, -6, and 2. Okay, so therefore we would end up having what? We'd end up having 8, -2.5, -3, and 1. So 8 times 1 minus -3 times -3.5. How much would that be? So in this case, 8 times 1 minus -3 times -3.5. So it would give us 1 over 2. Okay, the answer is just 1 over 2. So therefore our J1, okay, should be equivalent to J inverse, which is just 1 over 2. Another thing very interesting of the inverse transformation, yeah, the J inverse, okay, multiply the original J should give us 1. Okay, that's a very important thing to have. So in this case, it's just 1 over 2 multiplied by 2, which clearly gets 1. Okay, so yeah, that's pretty much it for Jacobian actually. So let me find a problem and we try to solve it together. Yes, let me try to find some problems actually, and let's see how we can solve them. I need to a little bit dig to my book first. Okay. Okay. So let me look to my book first. Let's see if we have any Jacobian problems to tackle. Where okay. Let me see if we have any examples here. Okay, I found one actually. Let's try the fraction out. So we're given a case where x, yes, so x can be expressed in terms of, let me use a yellow by the way, I'll just stick to yellow for now. So x can be expressed in terms of u 1 minus v, and y can be expressed in terms of u v. Okay, right? They want us to verify that del xy, okay, over del uv, okay, multiplies with del uv over del xy is equals to 1. So you can see that this is the original Jacobian, right? This is the original Jacobian that we're talking about, J, and this is basically J1, okay, the inverse transformation. So you want to see if we can get 1 or not. Okay, they want us to verify that. Okay, so what I'm gonna do is I'm gonna let you guys have a try this problem, try to pause the video and try to, you know, solve this problem. Okay, so assuming that you guys have tried this problem, let's try to solve it together. So I'm going to erase this, right? Okay. First things first, let's find del x y over del u v. Okay, so it's quite straightforward. It's just simply x over u, x v, y u, y v. Okay, find the Jacobian of that. So xu is how much? Xu is just u. Sorry, not u. Sorry, my bad. It's supposed to be. Sorry. Okay. Xu would be just 1 minus v. Okay. Xv would be negative u. Okay. If you want to simplify the equation, let's just double check. It's just u minus uv. Okay. Hopefully it makes sense. For yu, it's just v. For yv, is just u. Okay. So once you find the determinant, it's just u 1 minus v. Okay, and here is minus, so it becomes v times negative u. So it'll just simply be u 1 minus v plus uv. Okay, that's basically your Jacobian. So this is your Jacobian. So I'm just gonna write it in blue color, right, just so that we don't get confused. It's just u 1 minus v plus uv. Okay, we leave it at that. Now let's find the inverse transformation. Okay, so before we do that, before we actually find the inverse transformation, actually we need to rearrange the equations a bit. Okay, so to rearrange the equations, so first and foremost, x equals to u minus uv, and y is equals to uv, right? So we can say that v is equals to 1 over u y. Okay, so if I substitute this equation number 2, yeah, and this equation number 1, if I were to substitute equation 2 in 1, okay, what would I have gotten? I would have gotten here x equals to u minus u, then here you have 1 over u y, correct? So of course what would happen is that we can cancel out these u, right? Straight away becomes 1. So therefore we'll have here x is equals to u minus y, therefore u equals to x plus y. Okay, so this is your function number 3. We'll leave it untouched. Okay, and I'm of course gonna substitute function 3 in 2. So v would be equals to 1 over x plus y times with y, which is just equals to y over x plus y. So this is equation number 4. Okay, so taking equations 4 and 3, yeah, let's erase the other ones obviously because I don't want to create so much confusion. So this is our inverse transformation. Okay, so I'm going to write in green. Okay, so that means our u is obviously x plus y, our v is just simply y over x plus y. Okay, okay, so that being said, let's find the Jacobian inverse, which is just equivalent to ux uy vx vy. So in this case, ux is what? Ux is just y. Uy is just, actually sorry, ux is just 1, to be honest with you. Okay, ux is just 1 because we differentiate with respect to x, it becomes 1. Y is a constant. Uy also the same. Vx. Okay, now this is interesting, yeah. So you can treat this right? If in differentiating respect to x, it's just 1 over x plus 1. Or in other words, it's just simply x plus 1, right, to the power of negative 1. Okay, when you differentiate it, you get negative x plus 1 to the power of negative 2 times 1. Okay, so in this case, when we differentiate for this, right, we'll have a negative sign, so it become negative y, okay, become x plus y to the power of negative 2. Okay, yeah, that's about it actually for Vx, because y is like a constant technically. Okay, and for Vy, this one I have to do a bit of quotient rule actually. Okay, so this one involve a little bit of quotient rule. So if I'm going to do quotient rule, by the way, if I'm taking this as my let me just write it orange. If I take this as my V, this V is different by the way. This U and V are different. Yeah, these are not the Jacobian ones, so don't be confused actually. U and V, okay, this is for the quotient rule only. So in this case, what we'll end up having is Vy would be x plus y, okay, times 1 minus y times 1, okay, over x plus y squared. So in other words, it just becomes x, because you know x plus y minus y over x plus y squared. In other words, it's just simply x over x plus y squared. Okay, in other words, you can also write it like that. So x over x plus y to the power of negative 2. Okay, so with that being said and done, okay, we find determinant is just simply negative y over x plus y squared plus x over x plus y squared, which we can just write it like this basically. So this is x minus y over x plus y squared. Okay, so if I erase all of this, okay, what we'll end up having is so become x minus y over x plus y squared, and I can express it in terms of u and v actually, alright, which would be something like this. So it would be just u minus uv, okay, minus uv over u minus uv plus uv squared. So what does it mean? It be u minus 2uv, okay, over u squared. This is your J1. And for your J also, I think we can simplify a little bit. It's just simply u minus uv plus uv, which is just equivalent to u. Okay, so with that being said, let's try to multiply these two together, right? So J multiply with J1, what would end up happening is that I'm gonna put the equal sign for this, so it will be just u, okay, wait, why I put you in yellow color, hold up, I'm gonna put u, okay, u times with u minus 2uv over u squared, okay, and of course once you eliminate it, you just remain u, so it become just u over 1 minus 2v over u. So therefore we're left with 1 minus 2v. I think something is not right here actually, because we're supposed to verify that we end up having a 1, not a 1 minus 2v. So I think there's something wrong here actually. There's something wrong with our methodology. To check back the original Jacobian. So let me check back first, the original Jacobian function that we did. So I'm going to erase this real quick. Let's just check the original Jacobian. Okay, so yeah. Jacobian is just xu, xv, yu, yv. Okay, so xu is just simply what? It's just 1 minus v. Xv would be negative 1, and then yu would be yu would be v. Yu would be v, and yv would be u. Okay, so you end up having 1 minus v u plus v. If that makes any sense. Okay, so it'd be just u minus uv plus v. Okay, so it's a bit different. So our answer previously wasn't right. Let's try with this one. So this is our Jacobian, which is just simply u plus v minus uv. Okay, and I'm gonna erase. Let me just erase this. This is a bit distracting, by the way. Okay, leave it as it is, and then we multiply these two together. Let's see if we get the same, if we get the results or not. So I'm going to use yellow, by the way. I'm going to stick to yellow. So j times j1 should be u plus v minus uv times with u minus 2uv over u squared. You still don't get the right answer straight away, which is quite unusual for us. Let me check. Why is that a mistake? I think our J is a mistake actually. So let me revise J one more time. Supposedly it's xu would become what? 1 minus v. Okay, whereas xv would become negative u. Negative u. Okay, that's my mistake was there. And yu would become v. Yv would become u. So it would be just u minus uv minus, so it should be u minus uv plus uv. So the answer is u. Okay, then I think our j1 might be a mistake actually. So that means our j is supposedly u. Okay, then going back to j1, I think the j1 actually has an error in it. So let me try to fix it up. U minus u minus v, u minus 2 minus uv, u squared. No, I think it's a mistake. It should have been a plus, I believe. But let me check. Let me try to resolve this. Okay. Okay, so for J1, then just simply ux, uy, vx, vy. Okay, so ux will be how much? Ux will just become 1. Uy also become 1. Vx is just negative, right? Negative y over x plus y squared. Okay, I think I'll write a bit more nicely. So right nicely would become negative y over x plus y power of negative 2. Okay. For the case of vy, if you're differentiating, so it is just simply x plus y, okay, times 1 minus over right here, actually let me just write here real quick. So vy would be x plus y times 1 minus y times 1 just becomes x. So it just simply becomes like this. So it's x. Okay, that's where my mistake was. Okay, it was during the matrix operation. Okay, I found it now. Okay, so you'll end up having x over x plus y squared minus negative 1 negative y over x plus y squared. So therefore you will end up having x plus y over x plus y squared. Okay, so therefore your J1 would be, and you can actually simplify this even further also, by the way. So it's just gonna be x plus y, right? And this is 1. So I'm gonna be very quick. It is gonna be 1 over x plus y, and you can write it down as just 1 over, you know, x is just u minus uv plus uv, which is just 1 over u. Okay, so therefore, therefore from all of this we can actually show that we can actually finally prove that J1 times with J, which is J, is equivalent to U times with 1 over U, which will obviously give us 1. So this is already proven. Okay, it's already proved. Okay, so yeah, this is just one example, and I know it took a little bit of time. Sorry about that, because I made a small mistake, a very careless mistake. So please do be careful when you're doing your matrix operations. So let's go to one more question actually, before I think we can conclude about Jacobian. Let me erase this actually. Okay, so let's see. What's the question actually? Okay, so let's say if we are given in this form, right, to say that, let's say x was in terms of u square minus v square, and y was expressed as 2uv. Okay, the question wants us to find the Jacobian. Find the Jacobian of x and y with respect to u and v. Okay, so with respect to u and v. Okay, so find the Jacobian of x and y with respect to u and v. So I will allow you guys to pause this video for a bit and try to attempt at this question. Okay. Okay, so assuming you guys have already tried this question, actually it's very simple. So they want to find the Jacobian of x and y, so d del xy over del uv. Okay, which is very straightforward. It's just simply xu, xv, yu, yv. Okay. The del xu would be just 2u, xv would have been negative 2v. Okay, yu would have been 2v, and yv would have been 2u. Okay, so as you solve this problem, it's pretty straightforward. It's just simply 2u times 2u minus 2v times negative 2v, so it become 4u squared plus 4v squared. Okay, so that's pretty much about it actually. And so yeah guys, that's about it. So thanks for watching actually this series. So that's about all for partial differentials, right? Hopefully the video actually helped you understand Jacobian. And yeah, we'll be doing further content soon, probably more on other topics like vectors and matrices. Okay, so yeah, and of course integration and so on. Okay, so yeah, that's all. Thanks once again.